This recording is for Algebra 1A. It would have been on the Tuesday and Wednesday that were November 1st and November 2nd, depending on which period you're in. So we discussed a new concept in functions. We're still dealing with functions. We just had our quiz on how to tell if a set of data, a relation, is a function or not. We also talked about how to evaluate a function, whether it be an equation or a graph, and we talked about domain and range. So this is the next lesson in that topic. So we're going to talk about what's called linearity and continuity, but I'm going to just call it continuous or discrete graphs, or data. Really, it's the data is on a graph, but it's really, we're still talking about data. We're always talking about data, X and Y values. So this is pretty much the whole lesson. I don't understand why I cannot zoom in or out. I guess I can only zoom. Let me see if I can show more of this. Oh, by the way, this is on page 79 of your book pages, so you should have these torn out already. So if you just want to look on that page, you can see this whole diagram at one time. I unfortunately can't put the whole diagram up there, really. That's not going to do anything. So you can scroll up and down if you need to see it or look at your book pages, but we're talking about discrete and continuous functions. Or again, remember, functions are just a certain type of data. So it's not an extremely intense lesson. There's no real calculations or anything. There are definitely some notes and there are some things that you're going to have to remember, but there's not a lot of calculations like solving equations. So when it comes to discrete data, the definition of that is that we have individual ordered pairs as our data. So if you look at this graph, the data is in the form of, oh, why can I not zoom in and all? Oh, hold on. The data is in the form of individual X and Y points, X and Y ordered pairs. So there are, what, 1, 2, 3, 4, 5 ordered pairs in this particular graph. I'm talking about this graph right here, by the way, over here. And anytime you have a graph that looks like that, you call that a discrete set of data, or discrete function, really. So we'll talk in a minute about kind of an X range and a Y range, like what's the domain and range. For this, though, particular graph, it's just what we already did. We did domain and range from individual points on a graph, individual ordered pairs. So nothing changes for the domain and range on that. So if I come back out and if I scroll down, you can see it's just the set of individual values, You take all of the X values for the domain, you put them in order from smallest to largest, and you don't repeat any of them. And then you do the same thing for the range, only you use the Y values, put them in order from smallest to largest, and don't repeat anything. So nothing really that different for domain and range for a discrete graph. Now for the next graph, we would call this a continuous function. So all of the points are connected. So from the time you start graphing it, you can connect every single data point. There are basically there's no gaps in the data, no breaks in the data at all. So if we look at this graph, it just looks like a continuous line, thus the name continuous function. There's no breaks at all. It continues forever. It will go on forever up and to the right. It will go on forever up and to the right. That's continuous. Now, when it comes to domain and range, that gets a little bit trickier. Domain, again, is all of the X values. So if we're talking about all of the X values, that means what are the possible X values for this function? So basically, where will this graph be either above or below the X axis? Now, in this case, this graph will continue forever to the left. It will continue forever to the right. And we can already see that it's either above or below the X-axis through this range right here. So somewhere around -5 all the way through +5. And then it'll continue to go left and right from there. So in this case, there's no spot on the graph where this line, this set of data, would not be above or below the graph, above or below the x-axis. And I know that's confusing. It's hard to do on a video. So when we talk about what is the domain, it's all of the x values. There, again, there's no x value that this line would not be above or below. No x value that we couldn't pair up with a y value somewhere on this line. It may take us a long time to get all the way out to the negative infinity or all the way out to the positive infinity, but we would eventually get there because this arrow shows it's still going up and to the left forever, and this arrow shows it's going up and to the right forever. So from a standpoint of the domain, it's all real numbers. Like I said, every x value that exists. We talked in class about how to draw that. You could say it's from negative infinity on the left, and then x would be in the middle, and then positive infinity would be on the right. So again, all real numbers will work there. That's the way you'll normally see. Now, it's probably a little bit easier to understand what I was talking about when we look at the y values. So for the range, again, the range is made up of y values. We want to see where would this line, this is the data. Remember, the blue line is data. All the other lines are just imaginary lines. The y-axis is just imaginary. It's an imaginary number line. The x-axis is just an imaginary number line. And then all these grid lines are just imaginary. So when I talk about the line on the graph, I'm only talking about this blue line, which is the data. So we want to know for the range, where is this line either left or right of the y-axis? And if it's both, that's fine also. If it's both left and right, that counts. Well, as you can see, all of this area inside the graph is either left or right or both of the y-axis. Down here, though, we don't have any data that is left or right of the axis. So basically below -5, you could guess. I'm assuming that's probably -5. We don't know exactly. But there is no data below -5. So for the range, we would say any value greater than or equal to -5 is the range. So y, since that's what the range values come from, y would have to be greater than or equal to -5. There's only one real, so I guess they didn't even give you that because they don't know the 5, but there is one interval of real numbers. So that would again be y is greater than or equal to -5. So the last one then is if it's not discrete, so if it's not just a bunch of points on the graph, if it's not one continuous line. Oh, by the way, the line does not have to be curved. It can be a straight line. It could actually be a line with sharp angles in it, as long as it's continuous and there are no breaks in the data, no gaps. When we get over here, we can clearly see that there is a gap in the data, a big gap, and it doesn't have to be a big gap. But if there's no continuous line, then that is neither discrete nor continuous. And then for the domain and range, that varies. If you really wanted to get specific, you could say x could be less than about -5 again, because again, this line right here is directly underneath -5 for the domain. This line right here is directly above +5 for the domain. So you could say x could be less than or equal to -5 or greater than or equal to +5. That would be the domain. For the range, kind of similar. Where is the data either left or right of the y-axis? Well, it's right of the y-axis greater than 5. It's left of the y-axis less than -5. So again, your range is kind of the same. Your range could be y is less than or equal to -5 or y is greater than or equal to +5. I don't know. They didn't really get into specifics, so hopefully the district EOC next year won't get into specifics. But you'll learn this again in algebra, and they'll probably go into more data or into more detail in. So that's kind of in a nutshell. That's your discrete, continuous, or neither functions. So that will be on your quiz. There'll be a section where I give you some graphs, and you'll just tell me is it discrete, continuous, or neither. So I think that's everything on that page. So the other thing that we did is we talked about nonlinear or linear. So I did some questioning in class. I can't really do that in the video. But if you think about the word linear, it's got the word line in it, right? So maybe that helps you remember that linear means a straight line. So if you'll notice, all of these points are in an exactly straight line. So that would be a linear function if we looked at a graph. So anytime you see a absolutely straight line on a graph, that is a linear function. If you have a table, so right here you see we have a table. Well, in a table, the way you tell if it's linear is you say, okay, if the x values are all going up by 1, they're going up one at a time, 1, 2, 3, 4, 5. If I am adding the same number, if there is a pattern of addition, then that is a linear function. So in this case, I'm adding 1.4 or $1.40 every single time. 140 plus or 1.4 plus 150 is 2.9. If I add 1.4 again, I get 4.3. If I add 1.4 again, I get 5.7. If I add 1.4 again, I get 7.1. So again, but the key is the x values have got to be going up by 1 in order to do that little test to see if it's a linear function or not. We're going to do more examples of this in a minute. So let's see, determine continuity. So again, is that continuous, discrete, or neither? Well, I'll let you try to figure it out. You can pause. So now, since there is no break in that data, like there's no gap at all, you hopefully identified that as a continuous graph. As far as domain and range goes, then in this particular case, the domain would be all real values and the range would be all real values. This graph will continue to go left forever. It'll continue to go right forever, which means the domain is infinite, all real numbers. And hopefully, obviously, you see it will go up forever and down forever, which means every y value is a possible value, possible output. So all real numbers. This graph, I will let you determine it real quick. So hit pause. Hopefully you're back, and hopefully you said that is a neither. It is not discrete because it's not just individual points on a graph. It's definitely not continuous because we have breaks all over the place in the data. So if it's not continuous, if it's not discrete, it is neither. Next slide. So finally, this is just individual points. So, oh, I didn't tell you to pause it, but hopefully you identified that already. That is discrete. It is just individual ordered pairs on the graph, individual points. So that is discrete. Did not do any word problems. If we were identifying this, though, it's not a dead straight line. It's not exactly individual points. If you see right here, there is a connection from this point to the 0, 0. So even though that kind of looks discrete, it would actually be considered neither. Let's go. All right, so now we're into linear and nonlinear. So I might go to my actual, I don't even think I have it open yet. I'm gonna have to open it. But for linear and nonlinear, I gave you kind of a summary. From a graph, we said if it's an exactly straight line, a continuous straight line, really, it's a linear function. If it is a continuous curved line in any way, it's a non-linear function. So linear would mean a straight line on a graph. Now, if we had an equation, here we go. If we have an equation, so this is an equation, just no numbers. If you don't see any exponents that are 2 or greater, so right here, there's no exponent on, and it's got to be on the x or the y. You don't see an exponent on the x or the y, then we're going to consider that that's a linear equation. Now, there are some exceptions. I'm not really going to cover exceptions in Algebra 1A. but you will probably see next year in algebra that they will have sometimes when there's not an exponent of 2 or higher, so like an exponent of 2 or 3 or 4 or higher. There are some situations where the line wouldn't necessarily be an exactly dead straight line. But for 1A, we're just going to we're only going to talk about situations where you either have, like here, an exponent of 2 or higher on one of the variables, or you don't, like this particular equation here. And we're going to say this is linear. We're going to say this is nonlinear. Sometimes, again, you can have situations where there is no exponent of 2 or higher, but it's nonlinear. Don't worry about that for now. You'll go over that in algebra 1. So here is an equation. This is an equation of a line. It's y equals mx plus b format. There is no exponent that is greater than a 2. If you don't understand what I'm saying by greater than a 2, nothing is raised to the second power or higher than the second power. Therefore, this is a linear equation. So here we definitely have an exponent of 2. So we have another exponent of 2 also. So this would be a nonlinear equation. Oh. Boy, I didn't notice this in class. I think this is actually a trick question. This is actually, I believe, a linear equation. What I didn't notice in class is that this will actually cancel out. This is 3x squared subtract. And then even though we have an x squared, we have an exponent of 2, this term is also going to be 3x squared. So 3x squared subtract 3x squared means that the x squared actually goes away. And therefore you don't have an exponent anymore. You would not have an exponent greater than 2. That's a little tricky. You're not gonna have to worry about anything like that on my quiz. So I'm not super worried about the fact that I didn't catch it before. If they do something like that on an FSA or something, that's just gonna be pretty difficult to catch, I think, for a lot of you. But anyway, just for now, I think it's pretty safe to assume we have an exponent of 2 or higher, that it's going to be a nonlinear function. If you don't see any exponents of 2 or higher, then it is a linear function. We're going to stick with that for now. Again, exponent of 2 or higher, so that is going to be a nonlinear function. So I think we're probably going to move on. Again, exponent of 2 or higher, so nonlinear. Same thing. So again, from a table, if we want to find out, is this a linear function or not? We need the values where x is increasing by 1. So if you'll notice, we have some values in between where x did not increase by 1. It only increased by a half. You would have to ignore those rows. So you'd ignore this row at 0.5, you'd ignore this row at 1.5, ignore this row at 2.5. Only look at where it goes 0, 1, 2, 3. And between those rows, see if we're adding the same thing. Well, from 2 to 46, we added 44. From 46 to 58, we only added 12. So as soon as we don't add the same number, we can say it's nonlinear. We don't even need to keep going and checking the next line to see if we added more, if we added the same amount. As soon as the pattern is broken, the pattern of addition is broken, you're done. It's nonlinear. It has to have a pattern of addition, the same pattern of addition all the way through the table. Again, the key is, though, make sure you're only looking at where the x values are going up by 1. 0, 1, 2, 3. That's it. So I think I'm probably going to go over to, oh no, we did do these. All right, so I want you to try to figure out what the what the answer is. Are these tables linear or nonlinear? Now, if you'll notice, the tables are not going up by 1. The x values are not just going up by 1. Boy, it's going to be difficult to show you on this. I'll have to go over to the other one in a minute, but try to figure it out from here. Oh, tell you what, I'm going to come back to that because I need to show you this other thing first. Oh, I can't let you see my secret flag football plays. That's not even plays there. Just kidding. All right, so let's find a table like what we worked on in class real quick. Out. So not that one. Here we go. All right, so here's an example of when you do not have the x values going up by 1. So since the x values are not going up by 1, we can't just look at the y. Oh, and this is, by the way, a horizontal table, obviously. It's not vertical. X values will always be the values on the top. Y values will always be on the bottom. So therefore, these are input numbers on the top. These are output numbers on the bottom. So what we need to do in this situation, since we do not have values that are going up by 1 in the x values column, we are going to create a table where they do go up by 1. We'll learn a formula later for doing this, but for now, I want you to kind of do it the more intuitive way. I'm going to create a table that's vertical, so I'm just going to kind of flip it around to be vertical. Do it in blue. So I'm going to say these are my x values, these are my y values, and I'm going to start with 2, and then I'm going to go up by 1. Even though that's not the way the table looks, that's the way that we have to. Oh, I just did it wrong. That's the way, oh man. That's the way we have to see the x values if we want to use the method I just showed you. So 9, 10, there we go, and 11. So those are all the x values that would make my table look like it was going up 1 at a time for the x values. So from 2 to 11 with no points in between where we're skipping more than 1 value. Now that I have that, I go to the y column and I fill in all of my y values that I have in the table. So for an x value of 2, I have 5. For an x value of 5, I have 14. So I come down here to where the x value is 5 and I write 14. For an x value of 9, I come down here and I write 26. And then for an x value of 11, I come down here and I write 32. So if you'll notice, I have some gaps now. I have gaps at 3, 4, 6, 7, and 10. Here's what you have to try to do. You have to try to find a consistent number that you can add to this first row. And if you can add that same number every single time to the y values, and if you land right on 14, and if you land right on 26 here, and if you land right on 32 here, then it is a linear table. You were just adding the same number every single time to go from 5 to 32 underneath the y column. So just as an example that doesn't work, I'll show you what I mean. Actually, I'll show you a couple. Let's say I thought the pattern was going up by 1. Right? Well, if I added 1 to 5, I'd get 6. If I added 1 to 6, I'd get 7. Well, if I add 1 to 7, I don't get 14. So I don't land on the appropriate y value 14. So that doesn't work. So I go backwards and I try it again. Let's add 2. All right, so if I add 2 to 5, I get 7. If I add 2 to 7, I get 9. If I add 2 to 9, I get 11. Well, again, I don't land on 14, so that can't be the pattern. And again, there may not be a pattern because it may not be a linear function, but we're looking for a pattern. We're trying to just figure out if there's a pattern. So let's try 3. 5 plus 3 is 8. 8 plus 3 is 11. Oh, look at that. 11 plus 3 is 14. That's a good sign. So let's keep adding 3 and see if I hit the other two numbers, 26 and 32. So 3 plus 14 is 17. 17 plus 3 is 20. 20 plus 3 is 23. And look at that. 23 plus 3 is 26. So I hit that one more time. If I add 3, I get 29. If I add 3 again, I hit 32. So yes, I added 3 every single time. That is a linear function. It has a pattern of addition throughout the entire table for the y values when, and this is the key, when the x values are all going up by 1. So it's a plus 3 in the y values, y column. Plus 3 in the y column when x is going up by 1. But we had to create that new table, because in the original table, the x values were not going up by 1. So there is another way to do it, which we'll talk about later in the course. Sometimes this way is actually faster than the other way, but the other way will work, and you really kind of have to use the other way if you have a lot of decimal numbers in your table. Oh, sometimes your pattern could be a decimal, by the way. You might find that you need to add a number that isn't just a nice round integer like 3 or 2 or 4, or a negative number. You have to add something like 1.5 or 1.2 or 2.7 or something like that. So keep in mind, you could be adding a decimal as your pattern. I believe that was all we did in class for that. We did linear and nonlinear, and then we did discrete, continuous, and meter. So we talked a little bit about the X and Y intercept, I believe, on this particular lesson, but then we did a longer lesson the next class, so I'm not going to worry about that in this particular video. So you can just watch the next video for the X and Y intercept information.